Have you ever wondered how nuclear facilities deal with the intricate task of allocating resources efficiently? Imagine a bustling control room, filled with the hum of computers and the murmurs of dedicated scientists. Among them is Dr. Emily, a nuclear physicist, tasked with the challenging job of allocating mixture numbers for the Kino model. Now you might be asking, what exactly is this Kino model? It's a critical tool used in nuclear facilities to analyze neutron multiplication. The model requires unique mixture numbers for each structural material, but allocation is not a walk in the park. It's like solving a complex puzzle, with each piece needing to fit perfectly. The challenge lies in ensuring that each structural material gets a unique number. But here's the catch. There are constraints. The available mixture numbers are not infinite, and the allocation needs to be done in a way that doesn't compromise the integrity of the model. It's a delicate balance requiring rigorous attention to detail, and even the slightest misstep can lead to complications. And the stakes? They're high. If the mixture numbers are not allocated correctly, it could lead to erroneous results in the Kino model, potentially impacting the overall criticality safety calculations. In layman's terms, it could compromise the safety of the facility and its personnel. As Dr. Emily and her team grapple with this complex task, the tension is palpable. They're acutely aware of the importance of their work and the implications of getting it wrong. And then, just when they think they're making progress, the alarm suddenly blares. They realize something is wrong with the criticality calculations. As the room descends into chaos, they know they are facing a significant allocation challenge. It's a race against time, and they must act swiftly to rectify the situation. But can they do it? That's a story for the next scene. With the safety of the nuclear facility at stake, quick and precise action is needed. In the bustling control room, a team of expert nuclear physicists led by Dr. Emily is facing an allocation dilemma. The mixture numbers, critical to the operation of the Kino model, have been wrongly allocated. The result? Discrepancies in the criticality calculations, a potential threat to the facility's safety. The room is filled with a tense silence, punctuated only by the low hum of the computers and the occasional murmur of the scientists, deep in thought. At the center of it all is Dr. Emily, her fingers flying over the keyboard as she works to rectify the allocation issue. The task is like a high-stakes game of chess, each move calculated with precision, each decision carrying immense weight. Beside her, Dr. John is closely monitoring the situation, his brow furrowed in concentration. Time seems to stand still as they work, their minds racing to find a solution. The constraints are stringent, the margin for error non-existent, but failure is not an option, not when the safety of the facility, and everyone within it, hangs in the balance. Each adjustment to the mixture numbers needs to be perfect, each allocation fitting seamlessly into the model like pieces of a complex puzzle. It's a painstaking process, one that requires not just technical expertise but also an unwavering dedication to accuracy and safety. The tension in the room escalates, the air almost crackling with anticipation as Dr. Emily makes the final adjustments. It's a moment of truth, a test of their collective knowledge, skill, and resilience. And then, finally, after what feels like an eternity, Dr. Emily leans back, her face reflecting a mixture of relief and satisfaction. Finally, after intense work, Dr. Emily announces that the mixture numbers have been reallocated according to the constraints. This is a moment of triumph, not just for Dr. Emily and her team, but for the entire facility, a testament to the power of meticulous planning, precision, and unwavering dedication to safety. But the job isn't done yet. The criticality calculations need to be rerun. You can almost hear the collective intake of breath as Dr. Emily and her team wait with bated anticipation. The room is tense, the air thick with the weight of responsibility. In the world of nuclear physics, there's no room for error. The stakes are sky high, and this team, led by the unflappable Dr. Emily, understands that better than anyone. They've dedicated their careers, their lives, to ensuring the safety of this facility. As the calculations rerun, there's a quiet hum of activity. The team is monitoring the process closely, their eyes glued to the screens, their minds filled with equations and constraints. Every number, every decimal point matters. Dr. Emily in particular is a picture of focus. Her fingers dance over the keyboard, her eyes scanning the data on the screen with razor-sharp precision. She's not just looking at numbers, she's reading a story. a story of atoms and particles, of energy and reactions. It's a complex tale, but one she spent years learning to decipher. In the control room, time seems to stand still. Every second feels like an eternity as they wait for the rerun to complete. But no one complains, no one fidgets. They're all too aware of the importance of their task. Finally, the calculations complete. The screens flash, the numbers stabilize, and a heavy silence descends upon the room. Everyone turns to Dr. Emily, waiting for her to interpret the results. She looks at the screen, then at her team, and smiles. It's a small, tired smile, but it's a smile nonetheless. "The calculations are stable," she announces, her voice barely more than a whisper. But it's enough. Relief washes over the team like a wave. They've done it. They've ensured the safety of the facility, of the people who depend on it. It's a victory, not just for them, but for the whole field of nuclear physics. As the calculations complete, a sense of relief washes over the team. The moment of truth has arrived. Have they resolved the allocation dilemma? In the nerve-wracking silence of the control room, the hum of the computer's processors is the only sound to be heard. The team's collective breath seems to hang in the air as they wait, their eyes glued to the screen. The data streams in, the numbers dancing across the monitor in an intricate ballet of science and technology. Finally, the tension snaps as Dr. Emily breaks into a relieved smile. "The mixture numbers," she announces, her voice echoing in the suddenly still room. "They're stable. We've corrected the imbalance." A wave of relief washes over the room, as tangible as a gust of wind. Dr. John lets out a breath he didn't realize he'd been holding, a smile spreading across his face. "Well done, team," he says, his voice filled with pride and relief. "We've successfully navigated the allocation dilemma." As the team members exchange smiles and nods of approval, it's clear that this is more than just a win for their facility. It's a testament to the power of critical thinking and meticulous planning. It's a reminder of the importance of their work and the potentially catastrophic consequences of even the smallest error. In the world of nuclear physics, precision isn't just a goal, it's a lifeline. As they look at the now stable criticality calculations, Dr. Emily and her team understand this better than anyone. The allocation dilemma was more than just a challenge. It was a stark reminder of the importance of their roles and the gravity of their responsibilities. As the tension eases and the room begins to bustle once again, there's a renewed sense of purpose in the air. They've faced a daunting challenge and emerged victorious. But more importantly, they've reaffirmed their commitment to safety and precision. With the criticality calculations now stable, Dr. Emily and her team have successfully resolved the allocation dilemma. The sense of accomplishment is palpable, but there's also a newfound respect for the precision and attention to detail required in their field. They know that the next challenge is always just around the corner, and they're ready to meet it head-on. A nuclear facility's operations may seem complex, but at its heart, it's all about careful planning and attention to detail. Reflecting on the events that unfolded in our story, we can see that the allocation dilemma was not just a test of technical knowledge, but also a testament to the importance of meticulous planning. The constraints that Dr. Emily and Dr. John faced were not just mathematical equations on a computer screen. They were real-world challenges that had direct implications on the safety of their facility. Their struggle to allocate mixture numbers for the Kino model was a puzzle of its own, requiring a delicate balance of precision and creativity. And when things didn't go as planned, it was their ability to adapt and think on their feet that saved the day. This is a valuable lesson for all of us, whether we're nuclear physicists or not. In any endeavor, the ability to plan, adapt, and pay attention to the details can make a world of difference. The allocation dilemma also underscored the importance of teamwork. It was not just Dr. Emily or Dr. John's individual efforts, but their collective action that helped them navigate through the crisis. They leaned on each other's expertise, trusted each other's judgment, and worked together to find a solution. This is a reminder that no matter how complex a problem may seem, we are stronger when we tackle it together. But perhaps the most important lesson we can draw from this story is the relentless pursuit of safety. In a field where the stakes are as high as in a nuclear facility, there can be no room for error. The commitment to safety, the willingness to double-check and triple-check, to question and verify, is not just commendable, it is essential. It is the bedrock on which the integrity of the entire operation rests. In the end, it's clear, even in the complex world of nuclear physics, the key to success lies in the details.